Okay, in this example we are going to get lots of practice at calculating the rotational effect of a force, as well as dealing with how do we handle then an applied moment as opposed to applied forces. Now the context that we're oftentimes doing this is we're trying to figure out what the reaction is going to be. That means the forces over here at the support necessary so that no displacements in a particular direction are going to occur. So for instance, with a fixed end, we'd have no vertical movement, no horizontal movement, and no rotational effect over here. We got to have a set of forces and moments that will enable that to happen. So that's the context. Right now they just say find the total moment as a result of the applied loads with respect to point O. That's the natural thing that we're going to do. Now note again the definition of the moment of a force. M equals the perpendicular distance to the line of action of the force times the magnitude of the force. That perpendicular distance, that's hard to say, so we just call it a moment arm. Some of you might call it a lever arm. That's more of a physical specific situation. We more generally would call it a moment arm. And that's again the distance from the point of interest to the line of action of the force. This first one at A would be a vertical line of action. Now when we do this calculation, we've got to decide, do we want to use clockwise or counterclockwise as positive? So if I were to say put a pin here at O and I were to apply that force of 3 kilonewtons, that would tend to want to rotate the paper in a clockwise fashion. So that would be a plus. Right? Same thing would happen over here with the 1.4 kilonewton load. Applied that kind of force at this angle, and it's going to want to do the same thing. Now when we try to twist it, like we have here at B, then that's going to want to go in the other direction. Right? So that would be an example of a minus. So we'll have a plus, minus, plus here as we go along. So plus 1.8 meters is the perpendicular distance times the 3 kilonewton force minus 4 kilonewton meter moment. It's already in terms of a moment, so there's nothing that we have to do there. There's no moment arm. It already is the moment. It's on this side. You can't take D times the moment arm. That is meaningless. Right? So think about putting this on an air hockey table and then spinning it. Well, that's what you're doing. You're putting the couple on it. Right? And then we got to figure out what happens with this 1.4 kilonewton force. Now we have a lot of different options. One of it would be to try to work out a lot of geometry here to decide where what that perpendicular distance is. We could also use the principle of transmissibility to extend the line of action of the force. Right? And remember, it's D perpendicular times, which means go to the line of action of the force anywhere we want. Now you say, well, hold on a minute, mister, you're not drawing a perpendicular distance. You're right, but look what's going to happen as I go about with this approach. I'm going to slide that force down, and then I'm going to break it into 2 forces. Anything that I can do once, well, I could have just as much, I actually have twice as much fun doing it twice, right? So if I do that, look what cleverly happens. The x component is going to go right through point 0, and so then I only have the vertical component, and I can handle that just like I did with the force at A. It's just that the moment arm has gotten longer. So, of course, that force out here will be 1.4 kilonewtons times, then we got to swing it over. This is the 30 degrees, right? So that's 30 degrees. So that'd be cosine of 30 degrees. I don't even really care what the fx component is on that one. And so we'll have, let's see, we need that perpendicular distance, so that's going to be 1.8 plus the 0.6 to get us out to the bend. And then we've got this little triangle here that's got the 30 degrees. We want this, what amounts to be an hypotenuse down here. Alright, so if I want that, I want something bigger than the 1.2. So, whoops. That should not be 1.8 times anything. That's 1.8 plus 0.6 plus 1.2, and then I'm going to divide by the cosine of 30 degrees. That's all in meters. Right, then times the 1.4 kilonewtons times cosine 30. Right? Wow, that's a lot to do. Let's take the math step by step here in little pieces. 1.8 times 3 is 5.4 plus kilonewton meters. That's already larger than the applied moment of 4 kilonewton meters. And then I'm going to work this part out into little pieces just so you can see it all and still warm up to it if you're still not quite sure what's going on. 2.4 to get out to the bend plus 1.2 divided by 30 cosine. And that's a moment arm of 3.78. Oh, I'm going to go crazy here and go 5-6 meters. It's way too many significant digits, but I'm just going to choose to do that so that I don't lose any resolution here. And then 1.4 times 30 cosine would be the force component, 1.212 kilonewtons. Of course, I still actually have I haven't lost any resolution because it's all sitting here in my memory. So the whole moment effect then is 4.5898, which is 4.59. Add that to the 5.4 that we had. So 9.9898 minus the 4. So we end up with a number of 5.9898. And of course that's way too many significant digits. So we get that the moment about zero, the net, is going to be then 5.99 kilonewton meters. Now note we had a positive that ended up out of all this, in which we took clockwise here, but don't just leave it as positive. Now just clearly state that that is a clockwise moment at point 0, and that would be the applied effect. For equilibrium, you'd have to have the opposite of that to have no tendency for acceleration.